I welcome you again for this NPTEL online lectures on earthquake resistant design of foundations. And you may be aware that we was discussing this course under 5 module, and we are discussing a second module, that is on shallow foundation with 5 chapters. In the last lecture we have talked about raft foundation. You can say that was part A, and today we are going to the remaining part of the raft foundation we are going to discuss today. But before that, I will like to say that it will be better that we review very briefly so what we have discussed in the last. So, some of the slides which I am going to show, few of them you have already seen, and that will be little bit kind of a review only. So, you have this seen that we have taken this raft or mat foundation under these topics. We have already talked about introduction, design concept, codal provision, that is IS 2950. We was discussing and we will continue to discuss today also. Determination of Young's modulus ES has been already discussed, and determination of subgrade reaction K is also discussed. Rigidity of superstructure and foundation is also will be reviewed today. The last part, which is methods of analysis, and that is the bigger part than the this last one is this one topic is a major topic, and it is even bigger than the part A itself. So, today we are going to concentrate on methods of analysis exclusively, but before that let us review the under above 6 topics what we have discussed earlier. So, this was like introduction. So, I will skip that one, design concept also, and this then settlement in rafts, codal provisions. Now, when we talk about code, that is IS 2950, in this code there are appendix, there are 6 appendix. Appendix A, appendix B, C, D, E, F. So, we are going to discuss all these appendix. Appendix A we have already discussed, and just I will review rather than going in the detail of that due to the the limitation of the time. How to appendix E talks about determination of Young's modulus for the soil, that is ES, and this is important because this is required to calculate the settlements, and this is required for many other calculation. So, for the raft foundation. So, this we have discussed that it can be find out using 2 things, either one thing using plate load test where this equation is given, or it could be found using that what we say this cone penetration test. So, in the plate load test, ES is found from this equation which we have already discussed. The effect of the size of the plate is given in the top of this here on this slide, and here if you could see that if I check with this that under this is using the cone penetration test. So, this we have already discussed in the last lecture. Continually subgrade reaction, there are 2 tables are given in the code, one table 1 and table 2. Table 1 is for this based on the SPT values, and that is applicable for granular soils, or you can say the sandy soils, while table 2 is applicable for cohesive soils. This has been also discussed last time. Now, continue with that. Today we are going to talk about this design consideration also we have discussed, and the choice of raft type has been given in the slide, where you have see that there are 4 combination, where section A, section BB, section CC and DD has been shown. So, what you see in the first part A, it is simply raft, where you have kind of a footing as a flat, and on the top of you have columns. So, basically it is looks like a what you have seen in the rectangular combined footing, where the number of columns was 2 only, but here if you see there are 1, 2, 3, 4, 5 columns in one direction and 4 columns in another direction. So, these are like 5 columns. So, you could see that this is section on A, plan is shown on the top, but when this is called flat plate, plate below the raft is completely flat, there is no pedestal. But in the second case 1B, you have flat plate which is thickened under columns, and once this is thickened under columns, so then you have that means at the footing level you need to make the thickness of the footing larger at these junctions. So, you could see that thickness has been increased at these junctions. Then the same way the section CC is also for the case where you have 2 beam and slab, and they are also thickened under the bases. And in D case 1D, this is inverted. Instead of the base, the thickness has been increased at the top of the footing. This is flat plate with pedestals. So, this is also with pedestals, and this is also like the thickened, the similar. So, this depends on the the load coming from the top on the raft. So, in the simple case you can use AA, but as the load increases, as the requirements are different, then we can go section BB, CC, DD, and these are also given in the code IS 2950. Continue with that. Now, today we are going to the detailed out on methods of analysis. Briefly I have touched upon that one, but today now I am going to talk it in completely like that in a systematic way, that what is like we have. As we discussed in the last lecture also, that methods, there are two methods of analysis. One is called for what is called for rigid foundation, another is called for flexible foundation. So, we are going to discuss in the next slides that what we mean by rigid foundation and what we mean by flexible foundation. Once we say that we declare that foundation can be assumed rigid, then the method is very simple and we can go ahead with that. But if you that is the assumptions, and that is will be on the conservative side. But if it can come that we can assume safely that foundation is flexible, that in that case then we need to go for the second method, and then in the second method there are two parts which we will discuss later. So, let us discuss first what is the under article 5, that is methods of analysis. 5.1 is for rigid foundation, and the method used for rigid foundation is called conventional method. So, let us discuss the conventional methods which is applicable for rigid foundation. So, next few slides or next few discussions will be exclusively for rigid foundations. Once we get over with rigid foundation, then we will discuss flexible foundation. So, like in the rigid foundation, as we already discussed, that is a conventional method, and this is based on the assumption of linear distribution of contact pressure. And in the linear distribution of contact pressure, if you recall that when we discuss combined footing, for when we have the rectangular combined footing, then you have the uniform pressure distribution, and when we talk about trapezoidal combined footing, then you have the linear pressure distribution. That means, pressure under the footing is linearly varying from one end to another end, the variation is linear. So, when we can assume that this assumption may be this is the on what basis we can have. The basic assumptions for this method, that is the for rigid foundation or we say conventional method, are two, that foundation is rigid relative to the supporting soil and the compressible soil layer is relatively shallow. So, you have foundation one side, on another side you have the supporting soil. So, if there is a difference between the rigidity of the foundation and supporting soil, and that rigidity has been defined by a factor k, which we are going to discuss in the next slide. In that case, if you can say that this is rigid, then we can the foundation is relatively rigid. The second thing, the contact pressure distribution is assumed as a planar, such that the centroid of the contact pressure coincide with the line of action of the resultant force of all loads acting on the foundation. That means that the CG of the foundation should coincide with the resultant of the forces coming from the top. So, that is the second assumption. The first assumption is based on the relative rigidity between foundation and soil. Now, these are the these are the basic assumptions. These assumptions will be satisfied if either of the following two criteria are met out, and though we discussed these things I think in the last lecture also. So, I am repeating it again, that this structure behaves rigid due to the combined action of the superstructure and the foundation with a relative stiffness factor k which is greater than 0.5. For evaluation of k, the appendix C of the code, it is given in the, and we are going to discuss that. So, if the value of k is greater than 0.5, then this condition is satisfied and we can use this method. And if then another condition is the column spacing is less than 1.75 divided by the lambda, where this value of lambda is this will be coming in the appendix C. Here it is important to understand that for this method, either of these two conditions need to be satisfied. It is not necessary that both of the condition is satisfied. So, if either of this slide A or B is satisfied, then we can use this method which is called rigid foundations or conventional method. Okay. Now, let us see what is given in the appendix C. So, to calculate the value of k, and to calculate the value of lambda. Before we use appendix C, you see the figure given on the here, which is elevation. So, you have a raft foundation, and on the top of raft there are 4 columns, and a 3-story, you can say 3-story building, ground floor, first floor and second floor. Then the notations are listed here. Capital B is the length or width of a structure in bending direction from one end to another end, while small l is spacing of the column between, that means between 2 columns. Somehow in this case it is assumed that there is uniform spacing between two simplification, that between these there are 4 columns, and out of these 4 columns the spacing between these are same, that is L. Then HU, you could see the HU here. HU is nothing but length of upper column, while HL is length of lower column. If I combined then together, then capital H, which is total height of the infilling, where infilling is done here, and in the ground floor there is no infilling. So, infilling is on the first floor and the second floor. Then what you have IB, which is moment of inertia of the beam, as mentioned given in the figure also, and IU is for upper column moment of inertia, and while IL is moment of inertia of lower column, while this IF is also moment of inertia of raft, that is we F is used foundation beam, raft or foundation beam. So, we have in this picture, in this figure, the 4 moment of inertia is shown, IU, IL, IB, IF, and HU, HL, and the dimensions are shown. Using these notations, we calculate what is called a rigidity of foundation, EI, flexural rigidity EI of the structure, and of any section may be estimated as here, and this will be for the structure, and then we find the value of K using the rigidity of the foundation. So, you could see that EI is given by this relation, which is on the right hand side. Now, in the right hand side, let me explain, the prime or use IU prime is nothing but the value of IU normalized with height HU, IB normalized with L will give IB prime, IL normalized with HL will give IL prime, and then finally IF normalized with B gives you IF prime. So, once we know these 4 IU prime, IB prime, IL prime, IF, we substitute here and get. If you see this equation, this bracketed quantity is ratio only, because you have IU here the same, and the B square and L square have the same units. So, this will be altogether will be dimensionless. Then E2 and IB are one factor, and EL and IL. EL is modulus of elasticity of the infilling material. So, L, see this is for infilling material has been used, and then you have E2. E2 is modulus of elasticity of the frame material. So, you have this these 2. So, EL and E2 is defined here, IL has been already defined, B and H has been already defined. So, using this relation you can find the value of EI, and EI is the flexural rigidity of the structure. And once the flexural rigidity of the structure is known using this equation, that is the product of E and I, then we can find the value of K, which is called relative stiffness factor, which is also discussed in the appendix C of the code, and relative stiffness factors are listed here. You could see that whether a structure behaves as rigid or flexible depends on the relative stiffness of the structure and the foundation of the soil. So, that is the ratio, you can say the stiffness EI value for structure divided by the EI value for the foundation. So, this is here for whole structure, K is EI versus ESB cube into A. Here what is A, and let us explain what is EI, we have already discussed. ES is Young's modulus of soil, which is also discussed. A and B are the dimensions which is listed here, where A is perpendicular dimensions and B is towards the bending axis. So, in these 2 directions, A, once you fix value of A and B, then the value of K can be found out from the whole structure. Then if you have for the rectangular raft or beam, then this equation can be simplified by simply assuming that the value of I is 1/12 AD cube, where D is the dimension of the structure, and if you substitute in this case in the top, then you get this relation that K is given by this relation E divided by ES D by B cube, and you could see that K on the, if you see the right hand side, that this is a ratio only, there is no dimension for k, dimensionless, this is ratio. So, this will be a ratio only. Then if you have the circular rafts, then simply what you can do, B equal to 2 r, if you substitute the B equal to 2 r, then these equations you get from the B. So, these are there. So, this was how we find the value of k. If value of k is less than 0.5, then we say that this is this is k should be greater than 0.5, then in that case we say reached that is like that 1 minute. Here you have this. So, this should be k should be greater than 0.5. So, this was for the case for ridged foundation. So, you have this ridged foundation here. And now once k is known, if this condition is satisfied, fine, then if not satisfied, then check the value of lambda, and lambda is given by kb for ECI, b and I has been already like that mentioned. Then once the value of lambda is found, then as we discussed in the last slide, then check this ratio 1.75 lambda. If column spacing is less than this value, then still we can use this method. Otherwise, if neither of these two conditions are satisfied, then we cannot use this rigid foundation method, and then we need to go for other method. Once knowing this, continue with this for this rigid foundation or conventional method, we need to understand the raft is analyzed as a whole in each of the two perpendicular directions, and in this method, once you say this method is applicable, you need to find the contact pressure distribution, and this is determined the procedure given in the appendix D of the code, and here is appendix D. The pressure distribution Q under the raft shall be determined by conventional method, and this is written in this equation. What in these equations are given? Q is total vertical load on the raft, A prime total area on the raft, and E x prime, E y prime, I x prime and I y are the eccentricity and moment of inertia about the principal axis through the centroid of the section, and they are given by these relations. So, what is this for I x prime? You use I x and I x y also. What is I x y? I x y is the polar that means double moment of area or of area about I x and y axis. So, that means if you can find the value of I x y, simply integration of dA along x y dA. So, this is along this. So, this will be the using this relation I x y can be found, and once I x y is known, then you can find the I x prime, I x y prime, E x prime and E y prime, which is given in these relations here. And once these are known, then one can calculate the pressure distribution Q under the raft in the conventional method, and this pressure distribution used for further calculation. The same equation which was given here, this can be simplified. This equation can be simplified for the rectangular footing. For conventional method, this was the equation which we have discussed. This equation for a rectangular raft, the equation is simplified where instead of A prime you have the area only A, and instead of prime quantities then you can be used the simple quantity, and A and B are the dimension in along the x and y direction respectively. If one or more of the values of Q are negative from these equations, either this equation or this equation as calculated by the above form, it indicates that the whole area of the foundation is not subjected to pressure and only part of the area is in contact with the soil, and the above formula will still hold good provided appropriate values of I x, I y, I x y, E x and are used with respect to the area in contact with the soil instead of the whole area. So, here a small correction, when if you get any negative value from this equation area, so that negative part negative area should be not used in the calculation. So, in that case if some Q values are coming negative, then instead of using whole area we use only the value of area A which is positive. So, that means because we need to be on the conservative side, otherwise it may be unsafe, you are using the whole area, even some parts are showing the negative. So, that means that the negative values or area corresponding to negative values need to be ignored. So, this was appendix D. Continue with this ridge foundation method, that there is an article 5.1.3 for the code. In cases of uniform conditions, when the variation in adjacent column loads and column spacing do not exceed 20% of the higher value, the raft may be divided into perpendicular strips of widths equal to the distance between mid span, and each strip may be analyzed as an independent beam with known column loads and known contact pressure. So, first thing is that we need to check whether this variation is should be less than 20%. If variation in column loads is less than 20%, then we divide into perpendicular strips in both directions, and these strips are between mid span, and each strip may be analyzed an independent beam with known column loads and known contact pressure. So, if these conditions are basically what is that we have discussed the what is called ridge foundations or conventional method, and if you have the beams in two directions running, then this simplify further your that this method analysis. How it is simplified? That variation in the column loads is not exceeding 20%, and in that case it says that the distance between mid span and each strip may be analyzed independent beam. So, this is the keyword that we can analyze as independent beams with known column loads and known contact pressures. So, rather than analyzing the complete raft together, we can analyze beam by beam independent beams. So, this was a genesis behind this. So, with this we are done with the what we call the ridge foundations or the conventional methods. Now, if both of the conditions are not satisfied, or either even one of the conditions is not satisfied for ridge foundation, then we need to consider the flexible foundation. Under flexible foundations, there are two methods, one is called simplified method, another is called the general method. So, under this category of flexible foundations, you have two. So, let us discuss the first one, simplified method, because if you are satisfied with the condition for this simplified method, then you no need to go for the general method. If this is not satisfied, then we go for general method. So, that means general method will be applicable for all cases, general method can be applied for anywhere, even for the, but that will be little complicated compared to this conventional method and the simplified method. In case of simplified method, it is assumed that the subgrade consists of an infinite array of individual elastic springs, each of which is not affected by others. So, this is important. That means, you are dividing subgrade, first of all subgrade or the soil has been divided into infinite array of individual elastic springs, and these springs are independent, means they are not affected, that one spring is not get affected by other spring. The spring constant is equal to the modulus of subgradation k. So, to find the value of spring constant, we need to use the value of k. How, what is the subgradation k? We have already discussed in the last lecture. The contact pressure at any point under the raft is therefore linearly proportional to the settlement at any point. The method may be used when the following conditions are satisfied. Now, what are the conditions for this method, for simplified method? The structure, that means combined action of superextended raft, may be considered as flexible, that means the factor, relative stiffness factor k should be less than 0.5. Variation in adjacent column loads does not exceed 20% of higher value, and here it is important to note that both of the conditions need to be satisfied. It is not either. So, first of all, that structure should be rigid, the value of k should be the structure should be flexible. So, value of k should be less than 0.5, and the variation in column load should not be more than 20%. While, so what is here? Let me summarize. In the conventional method, if you get the k is greater than 0.5, then you can use the conventional method. If the first, that is the first condition, if that is not satisfied, then you check the column like the load 1.75 divided by lambda spacing. If it is less than, still you can go for that method. But if neither of that condition is satisfied, then we come here. But if you come here, then to use this flexible method, simplified method, both of these conditions need to be satisfied, not only that one need to be satisfied. So, let us assume that this condition have satisfied. If this is satisfied, then we use the method given in appendix E. Let us see that what is appendix E. Appendix E gives the pressure distribution and moments below flexible foundation. Appendix D was giving pressure distribution for the ridge foundation. So, D is for rigid foundation while E is for flexible foundation. The contact pressure distribution is assumed linear with maximum value attained under the column and minimum at mid span. So, you have this under the columns there is maximum value of the contact pressure, while at the middle of the between two columns and that is good, that most of the contact pressure distribution, and that is simple, because most of the pressure is coming at below the columns. The contact pressure for the full width of the strip under an interior column load point I can be determined as given in figure 3a. There P I, which is the pressure distribution, and this is given from the right hand side, where capital P I and M I are, P I is you could see in this figure, if you see this figure 3a, this figure, if you see this figure, let me first explain this figure. In this figure the moment and pressure distribution for interior column is shown. So, you have this two columns, this interior column, three columns, that is P I, this is one this interior column, and these two are exterior column, P I minus 1 and P I plus 1. The distance between this interior and previous column is L subscript L, that means subscript L is left side, while this is L R. So, the subscript L stands for left side and R for right side. So, the distance to left side is L L, while distance towards the right hand side is L R. And so, P I is the this what you say this point load acting at the interior column. Then M I is the what you have M I here is basically this, you have this bending moment acting at this that the point of the same the interior column M I. So, let us say the P I and M I are known to us, and the problem in this case is to find the pressure distribution small P I. So, in this case this is nothing but small P I, and this small P I is given from this relation. So, in this relation L bar is nothing but average length of adjacent span. That means, you have both side spans divided by 2 will give you the values of average length of adjacent span, and then P I and M I are known. So, this under an interior column can be found from this relation. Continue with that. The minimum contact pressure for full width of the strip at the middle of the adjacent spans PML and PMR. So, which is also shown in the figure, and this is the for full width of the strip at the middle, that was at the interior column, but now we need to find the value of these PML, PMR and PM, which is like the shown in figure 3a. Again, if you see here sorry, this should be figure 3b. So, PML is here and PMR is shown here. Then you have this PM is will be the average of PML and PMR, where L, PML and PMR is calculated from these relations. Pi has been already, that contact pressure, small pi is also like that we have discussed. Then once you have this, then using this what we can find the distribution under, that was the Pi was the under interior column, while PML and PMR, L is for the left hand side, and you can say PML, M for mean value and L for the left side. So, the PML for the left hand side and for the right hand side, but both are mean value. But if you find rather than at the left hand side and the right hand side, then this should be also small, the small PM can be calculated from this relation, which is the average you get from these two, and LL and LR we have already discussed, that is shown in figure 3a, which we have discussed. Okay, so, we have done with this figure 3a and 3b also we have used. Now, continue with that moment and pressure distribution at exterior column. Earlier we discussed that interior column, in figure 3a it was for interior column, okay, and now you are going to discuss about exterior column. So, for exterior column what has been done, this is let us say this exterior column is PE, okay, while PI was for the interior column. The distance between exterior and interior column is L1 in this figure shown L1, while C is the distance up to which your this bending moment becomes 0. So, if you see the bending moment is maximum under the columns, and here in mid span, but then bending moment becomes 0 at this point. So, C distance has been shown in this case. So, L1 C has been shown in this figure, and what is given? Capital P and Pi, the load acting, and these columns are known to us. Now, we need to find this distribution, and for this distribution you have P under exterior column and in mid span Pm and at the end Pc. So, you have 3 values, small pc, pe and pm. So, how to calculate that? That has been given in the next slides. So, you have the P and Pc, P is at the exterior column and Pc at the end C point where you have this bending moment 0. So, these are given from these relations. P and Me is already given, C is the distance, small pm has been earlier we have already discussed. So, all things are on the right hand side is known. So, once all things are known, then you can calculate the value of P and Pc, and as we discuss what is P, Pm, and these things are shown in figure 3c we have already discussed. So, P and Pc are given from this relation, provided if condition A governs the moments. Here it need to be understood, there are two conditions. One condition A governs the moment, then we use these relation to calculate the value. But if condition B governs the moment, in that case we use this relation. Here P and Pc, there are two different equations, but in condition B the equation is same and Pc and Pe are given, they are same and they are given from this relation. Now, what is condition A, what is condition B, we are going to discuss in the next slides, and then if condition A is satisfied, use these relations, the top one. If condition B is satisfied, use this relation. Here before that like that how to calculate the moment, or for the moment the bending moment under an interior column which is located at I can be determined using this relation Mi Pi for lambda. Lambda we have already discussed, L bar has been already discussed. So, Pi is the interior load at the interior column. So, Mi can be calculated from this relation. Total moment is Mi plus m naught, where m naught is given from this relation, and that is L square by 48 PIL for Pm plus PIR. Here that if you see here that this has been shown here in this figure, that you have for one is for left side, another is for right side. So, you have for the left side L, R for right side, and Pm value is in between. So, once you have PIL, Pi 4 times of Pm and PIR, then divided by 48 into L square, this will give the moment. Once m naught is known from this equation, then we get total moment using m naught plus mmi. Okay. So, once you are find out this from total moment. Now, in the last slide we have discussed that there are two conditions, condition A and condition B. So, what are these conditions? So, they are listed here. Condition A is for this using this equation, and condition B. The bending moment Me under can be determined as the least of the bending moment, either you if you get this least value. So, that means if A is the least, then condition A is satisfied. Out of these two will, if B is least, then we go for the B condition. So, what you need to get the values of this bending moment using this relation. These both will give you bending moments, and these bending moments, once you find from bending moments from this equation and this equation, and compare the two moments. If you are getting the least from condition A, then we say condition A, we will go with condition A, and if you get from B, then we go for, if condition A is giving the least, then we use this relation, and if B is the least, then we use the another relation. So, this completes about appendix E for the code, and the appendix E, as we discuss, use what is called for the simplified method. As I mentioned that in under RIS foundation you have two methods, one is called simplified method, another is general method. So, if criteria for simplified method is not met out, then we go for the general method, and naturally for general method is the last method. If no criteria match, general method is general method which you can use for anywhere, if no, even if the conditions are like. So, idea is that the conventional method and simplified method, they are relatively simple than general method. Now, let us discuss what is general method. For the general case of a flexible foundation not satisfying the requirement of the simplified method, this may be used as we discussed, and this is based on closed form solution of elastic plate theory. Okay. So, you have elastic plate theory, and here plates on Winkler foundation takes into account the restraint on deflection of point provided by continuity of the foundation orthogonal direction. So, basically if you recall, in the simplified method we use elastic springs, but here we do not have spring, rather plates are used on Winkler foundation. So, the foundation will be treated as a Winkler foundation and the plates, and this takes into account the restraint on deflection provided by the continuity of the foundation in orthogonal direction. The distribution of deflection and contact pressure on the raft due to column load is determined the plate theory. Since the effect of column load on an elastic foundation is damped out rapidly, it is possible to determine the total effect at a point of all column loads within the zone of influence by the method of superposition. Here, because this is linear method, so we can use the superposition method. The computation of the effect of at any point may be restricted to columns of two adjoining bands in all directions, and this process is in appendix F. So, for the general method which we have discussed here, description. So, appendix F deals with that. Now, let us see what is appendix F, and then this appendix F says the closed form solution of elastic plate theory. For a flexible raft foundation with non-uniform column spacing, the spacing is not uniform, then also you can use the general method, and load intensity is not uniform. Solution of the differential equation governing the behavior of plates on elastic foundation, that is Winkler, gives radial moment Mr and tangential moment Me and deflection W. So, the radial moment is given by this relation, whereas you have this function Z3 prime, Z4 prime, and there are two functions are coming, and these are functions of R by L. What is R and what is L, we are going to discuss later. And so, that means radial moment is given from this relation, and then you have this tangential moment is given from this relation after using this radial and tangential moment, and then the, W is here. So, this should be tangential moment, this should be actually T, MT, radial and the tangential moment, this should be also same T. Then you have this W is given from this relation. Now, what are the Z3, Z4 and Z prime, we are going to discuss later. P is column load here in these equations, that is the column load, as this P was coming here, you could see that. And one thing is important to note, all these three equations, this one, they will give you the value for per unit width B equal to 1. That means, if you see the dimension on the right hand side and the left hand side, the right hand side is gives only the load force. So, to get the calculate the moment, you need to multiply with the width B. Same thing is for the second equation, and the last equation, this will also, because PL square and this later on if you see that this will be a ratio only. So, no deflection. So, if you multiply by B, then you will get corresponding deflection. So, what is here? Continue with that. So, P is column load, R is the distance of the point under investigation from column load along radius. So, R will be distance, and L is called radius of effective stiffness. So, R and L will have the same dimensions, if they are in centimeter, both will be in centimeter, otherwise in meter. So, ratio R by L will be dimensionless, but L, to find the value of L, you need to calculate this from this relation, that is d by k to the power 1 by 4. And once you know that from this ratio L is calculated, then your this function is ready, R by L and R by L. Now, issue is this, what is D here? D is called flexural residue of the foundation, which is given by this relation E B T cube 12 1 minus mu square, where T is thickness of the raft and B is equal to taken normally 1 here. So, assuming, because it is done for unit width, so B it is given only for dimension, but B is 1. So, if you check the dimension of this is Young's modulus multiply by I, and then you have modulus of subgradation K for footing of width B. That means, whatever modulus of subgradation you get, that should be multiplied by B to get the value of this K here. And once you got that, then what you will have, that unit D by K, K will be have the unit of E only, and so this once you do this, the unit of L will be same as the distance, or that means for R. and you get this. Now, Z3, Z3, Z4 they are given on the next slide, that is how to find. Here before that the shear, this is for the moments, you know these two equations are for moment and the third equation for deflection. Now, the fourth equation is for the shear. The shear Q per unit width of raft can be determined from this relation where P and L is already defined and Z4 prime are given. So, there are four functions Z3, Z3 prime, Z4 and Z4 prime. So, the values of that can be calculated from this graph where R by L is given on x axis, which is varying from 0 to 6, and according to once you select the value of R by L, then you read from this chart the functions of these four functions, these values of these four functions, and once values of these four functions are known, then we substitute back in these equations of appendix F, and then you calculate the what we call the moment, deflection and shear from this, and this moment, deflection and shear, they are used in the design of what is called flexible foundation of general method. So, this is complete all like for related to raft foundation, that methods of analysis we have discussed for both rigid foundations, which is conventional method, as well as for flexible foundations, which is two methods, simplified and general methods. And this is given, all the things are though given in the code, but it would be better to discuss, because raft foundation, as we discussed in the last lecture, is very important for earthquake loading. If your combined footing is then we go for the raft foundation. So, this completes the fourth chapter of module 2. Now, in the next lecture we are going to talk what is called the dynamic bearing capacity, and this is very important in the next lecture for the earthquake point of seismic consideration point of view, because that instead of bearing capacity, that how the bearing capacity gets changed when you consider the dynamic loads. Okay. Thank you very much. Thank you for your kind attention.